Did you ever notice that almost every function you learn in high school starts with y equals something? Y equals sine x, y equals the log of x, y equals x squared plus 2x plus 4, y equals 7/3 sine of 3x minus 7 plus 9. It almost seems unfair that the variable x gets stuck on the right hand side with all the junk, and the letter y gets to stay by itself on the left hand side. But why do we do that? Well, we've tried to tell you guys that, well, it doesn't have to be x and y, but it's an independent and a dependent variable. The goal is to be able to plug in an x value and get a y value. So it's normal that we have y by itself because we don't mind putting all the calculations in with the x variable, but at the end we just want to know what y is. So it's already set up for us. Y equals that answer. So our dependent variable should always be by itself on the left if we want to make things easier for ourselves to do, for example, a table of values or to graph it easily. I'm going to continue along with this equation to show you the rest of the transformations, but I'm going to change the y variable to f of x. That way it'll be more obvious which x value I'm plugging in for each y value. F of 0 is about 7.467, f of 1 is about 10.765, f of 2, f of 3, f of 4. There we go. There we've got our values. This is just a typical sinusoid that we've already learned how to graph pretty well. So let's review what we have in front of us. We have an equation, f of x equals 7/3 sine of 3x minus 7 plus 9. Here's the table of values that goes along with it, and here's the graph that goes along with it. What about a scenario? Let's just make a scenario so we kind of have in our head what sort of scenario would go along with this. So we're used to the Ferris wheel scenario, but any sort of turning object would work, or maybe waves, a wave pattern of some sort. But let's just say that let's call this time of 0. At time 0, there's something that's at a height of 7.467. At time 1, so let's say 1 minute later, it rises to a height of 10. Well, it goes all the way up to a height of a little above 10, and then it comes down to 10.765, and then it comes down and comes back up, and after 2 minutes, it's at 7.037. After 3 minutes, it's now at 11.122, and after 4 minutes, it's down to 6.763. Well, what happens if we get another scenario where you've got all the same heights, all the same situations, but maybe there's like a 4-minute delay. Maybe something happens and it delays this Ferris wheel for 4 minutes for some reason. Well, now we want these exact same heights, but we want at 4 minutes, we want the height of 7.467. After 5 minutes, we now want this. At 6 minutes, we want 7.037. At 7 minutes, we want 11.122. And at 8 minutes, we want this. So it's just a new situation. So our old scenario, our old graph, will no longer give the correct answers. Our old equation will give the answers for what would happen in the old scenario. We want a new equation that gives the exact same answers when we plug in the new numbers of 4, 5, 6, 7, and 8. So how would we accomplish this? All right, originally we plugged in a 0 for this x right here. So as you can see, it became a 0 for f of 0. And we ended up with a value of 7.467. That's because we did 3 times 0, which equals 0, minus 7. We took the sine of that, multiplied by 7/3, and added 9. Now we want to plug in the value of 4 right here for the x, but we still want to somehow get this to equal 0, even though we plugged in a 4. Well, if I just plug it into this equation, I'm going to get 12 here, and that's going to change my whole answer. So what we're going to do is we're going to modify this equation. We're going to say f of x equals 7/3 sine of 3. Now instead of putting x, we're going to put x minus 4, minus 7 and plus 9. And now watch what happens. When I plug in a 4 for x here, now the first thing that's going to happen is 4 minus 4, which is going to give me a 0, which will bring me right back to the equation of my f of 0 over here. If I plug into 5, now this 5 minus 4 will become a 1, which will give me the exact same answer as f of 1 previously, 10.765. Of course, f of 6 will now give me what the original f of 2 will give me, because 6 minus 4 is equal to 2. So this minus 4 is basically saying, hey, take the number that I'm putting in now, subtract 4, so it just seems like you're putting a 2 in there. So as soon as you put that minus 4, it's like you had originally just put a 2 in, and all the rest of the calculations will be the same as when you originally put a 2 in. So basically you're going to get the same answers as before, except you're required to put a number 4 bigger for each one of those numbers. Now my new table of values, instead of 0, 7.467 is now 4, 7.467. Instead of 1, 10.765, it's going to be 5, 10.6. Each one of these x values is now 4 larger than it used to be. If I plug in a 0 now, I'm not going to get the same answer as before. I'm going to get what I would have gotten before with a negative 4. So everything is moved over 4 to the right. Well, what does that do to the graph? Okay, well, now instead of 0, 7.467, we now have 4, 7.467. So this dot goes over here. Instead of 1 at 10.765, we now have 5. So this one goes over here. And every dot, as you can see, will move 4 to the right. This entire graph moves 4 to the right. And so when we look at the equation, when you put an x minus 4, what ends up happening is every dot moves 4 to the right. Here's the original equation, y equals 7/3 sine 3x minus 7 plus 9. Now what's going to happen here when I replace this x with x minus, let's say, 0.5. So before we had the 0.5 in here, I could plug in a 0, and this was just going to equal 0. Now I have to plug in a 0.5 for this thing to equal 0. So when I plug in a 0.5, I'm going to get the same value. And on the graph, if you look here, I used to plug in a 0 to get 7.467, and now I have to plug in a 0.5 to get 7.467 right here. And every point has moved over to the right by 0.5, because now the x value that you have to plug in to get the same y value is 0.5 greater. And of course that we can continue that along. Alright, now we got x minus 1, and all the values just go up by 1, and the graph just goes to the right by 1. So the purple graph just kind of moves to the right. And as I subtract more and more, the graph goes farther and farther to the right. Okay, so here's x minus 4, and as you can see, each dot has moved 4 to the right. And you can also see in the table of values, 0 has become 4, 1 has become 5, 2 has become 6, 3 has become 7, and 4 has become 8. And these coincide with our actual, see, 6, 7.037 is 6, 7.037. Now hopefully you realize right away that if I were to put a plus sign here, that would just be like that would be doing the opposite, right? So that would mean if I put x plus 4, then I would have to put a negative 4 here to make this 0, which means this whole graph would just move to the left. Okay. Now that doesn't just work for this one like for a sinusoid. Obviously, this will work for any type of graph you can think of. Here's a typical polynomial equation. Y equals negative 3x to the 4 plus 15x cubed plus 42x squared minus 108x minus 216. Now I want you to pause the video and try to figure out what would be the equation of the graph that's exactly the same graph, but moved 2.5 units to the left. So this blue graph here. So your red graph is this equation right here. What would be the equation of the blue graph? So the trick is, we know that on this graph at 4, we want the answer. So if I plug in a 4 here, I know that my y value is going to end up equaling like 200 and something. Okay. Now I want to be able to plug in a 1.5 to get the exact same value. So you just rewrite the equation, y equals -3, and you just put x plus 2.5 to the power of 4. Now when I plug in a 1.5 for x, this value is still going to be a 4, and you're going to get 4 to the power of 4, just like you would have in your original. So you're going to get the same value. Plus 15, well, you still need an x plus 2.5 here, because remember, we're only plugging in a 1.5, but we need it to get the same thing as if I had plugged in a 4 from before. So every single x in any equation, if you just want to move it over 2.5 to the left, all you do is you take every x in the entire equation, you replace it with x plus 2.5, and that will give you the exact same graph except moved over 2.5 to the left. So that's your answer. Y equals -3, x plus 2.5 to the power of 4, plus 15, x plus 2.5 to the power of 3, plus 42, x plus 2.5. Oh, that should be squared. Plus minus 108, x plus 2.5, minus 216. Now, of course, you can expand this and multiply it out, but there's no use doing that. You already have an equation that is perfectly fine and gives you the blue graph. Here's a rational equation, y equals x minus 3, x plus 2, x minus 5, x minus 7, x minus 9, all over x minus 3, x minus 1. I want to know the equation of this graph right here, which is the green one here, which is the same graph but moved to the right by 3. So it's every point is just moved to the right by 3. What exactly is the equation for that? Pause the video, write it down, and see if you get it right. Well, the solution is just to replace every x with x minus 3, which we have here, and this one looks a bit wonky. I think I will reduce it. So there you have it. This is the green graph. This is the blue graph. And as you see, it's just every x is just replaced with x minus 3. Here's an interesting graph. Y equals sine of the log of x squared to the base 2. What if I were to ask you to move this entire graph over 3 to the left? What would your new equation be? Give that a shot and come back to see if you get the right answer. Since we're moving 3 to the left, we simply want to replace the x value in the equation with x plus 3. That way, to get the same value of y, we're going to have to put in a value that's 3 less, so that when you add 3, it ends up being the exact same value as before. All right, so our new equation is y equals sine of the log of x plus 3 in brackets squared to the base 2. What if I want, with this graph again, but I want it to be 3 higher instead of 3 to the left? How would I move it 3 higher? Right, so pause the video and see if you can give me the equation of the exact same graph as this blue one, but 3 units higher than that. If moving a graph to the right requires me to just switch the x to an x minus however far we want to do it, and then moving it to the left just means switch the x with x plus however far we want to move it. Keep the brackets here. Then shouldn't moving it up and down be the same thing, but just switching the y? And it is. So if I want to make the graph go up, I want to make it go up by 3, I could simply replace y with y minus 3. Just like switching x in the positive direction, you just replace it with x minus 3. Well, switching y in the positive direction, you just switch it with y minus 3. And this makes sense because now these values that you get here, for example, right here on the graph, when x is 2, you get a value, this right here will give you a value of just a little bit less than 1. 2 comma 0 point something. But now that won't satisfy this new equation because it doesn't equal y anymore, it equals y minus 3. So in order to satisfy this new equation, y must be greater by 3. So we're going to say 2 comma 3 point something. Right? If y is 3 point something, well then y minus 3 is 0 point something, which is exactly what this right-hand side equals. So since this right-hand side is going to be your old y value, then when you switch to y minus 3, then for this equation to still be correct, the y value obviously has to be 3 greater, and that moves each point up by 3. There is one caveat with this, however. At the beginning of the video I told you we love to have y by itself. If I were to keep y minus 3 on the left, then plugging in x would sort of be a chore, because every time I end up with an answer to the right, I would have to add 3 to that answer in order to get my y value, because it's not supposed to be equal to y, it's supposed to be equal to y minus 3. So every time I get an answer, I have to say, oh, wait, first I have to add 3. Right? So we always want to get y by itself, right? So even though the transformation is y minus 3, that's the one we're looking for, we still want to rewrite this equation as y equals, we're going to add 3 to both sides, so sine of the log of x squared to the base 2, all in brackets, plus 3. So that's the big difference between moving things left and right, horizontally, and moving things vertically. When you move it vertically, there's an extra thing you have to do to get y by itself again, because y is supposed to be the dependent variable, right? And it kind of disguises it, right? So when you move things left and right, if you want to move it, 4 in the positive direction, you're going to have to put x minus 4. And it seems like it does the opposite when you move it up and down, because you end up with a plus there, but it's not really that's not really what's happening. You're actually doing a minus as well, but then when you bring it to the other side, it switches signs. Okay, quick challenge for you. I want my y equals sine of log x squared base 2 again, except this time I want it to go up 3 and to the left 3. So write the equation in the standard form, so I want y by itself, and I want the equation to be the same as my blue graph here, but I want it to go up 3 and to the left 3. So a vertical transformation up, a vertical translation up, which is a transformation, and a horizontal translation 3 to the left. All right, pause the video, write the equation, and come back to see if you've got the same equation as I get. Well, we've got our equation right here, and we want to move it to the left, so this x becomes x plus 3. And we also want to move it up, so the y is going to become y minus 3. And then we're going to bring the minus 3 to the right-hand side to get y by itself, and we have our new equation. This will, of course, work on any equation, because all you're doing is replacing the variable with the variable plus or minus something. So it's just making the variable forced to be bigger or smaller by that amount in order to have the same value. And so the entire graph is just going to move in that direction by that amount. Here's another challenge for you. Right here we have, this is sine of log of x squared base 2 plus 3. So this is like the original equation that we had, but moved up 3. Right? Now there's a point here, 3 comma 2.972. All right, for fun, let's say that after 3 days, there are 2.972 gallons of water left in my reservoir, in my water reservoir. Right? So maybe this graph is just showing me the water level of my water reservoir day after day. Well, what if I decided that I wanted a graph, the same graph of the same reservoir, but I wanted it to be hourly instead of daily? So instead of 3 comma 2.972, this would be hourly, so it would be, let's see, 72 hours later. So this would go all the way out to 72. And the value that's way down here at 1/24 represents 1 hour. And so now that we're doing it in hours, so that will stretch out all the way to 1. So then 1/24 will go to 1. So basically we're going to stretch this graph by a factor of 24 in the horizontal direction so that whatever value of 1/24, which used to represent 1 hour, moves all the way out to 1 in order to represent like 1 hour. So whatever the value in days were before will now be expressed in values of hours. So I want to know what's the new equation that will give me a graph that's stretched out by a factor of 24 in the horizontal direction. Now pause the video and come back when you think you have the right equation, and we'll see how you did. Keep in mind that the earlier version had a point of 3, 2.972, and when we stretched it by a factor of 24, so this represented 3 days. When we stretched it by a factor of 24, that point became 72, 2.972, because now we're talking about 72 hours. We're talking in hours now. And we also had a point of 1/24 originally, 1/24, 2.748. That was 1/24 of a day, so an hour. And now that we've stretched that by a factor of 24, that became 1, 2.748. So our new equation should satisfy the values 1, 2.748, the point that 1, 2.748, and the point 72, whereas this original equation should satisfy 1/24, 748, and 3, 2.972. So if you're clever, you could see that 3 times 24 is 72. So in order to get 72 in the equation, to plug in a 72 into the equation and have the same effect as what the 3 used to have, well, you just divide by 24. Right? So, and the same with 1 divided by 24 will give you 1/24. So if you just write a new equation of y equals sine of log base 2 of x over 24 in brackets squared plus 3. Well, now when you plug in a 72 for x, well, it'll divide by 24, which will give it 3. And you're going to do 3 squared log base 2 of 3, just like what you would have done with your original 3 in the original equation, which means you're going to get the same answer as what you would have gotten in the original equation, which is exactly what we want. So basically what we're saying is when you want to stretch by a factor of a, well, you just take all the x values in your equation and you divide them by a. In our case, we wanted to stretch our graph by a factor of 24, so we just took the x value that was in our equation and we divided it by 24. Remember to keep brackets around it as well, right? Because if this x is being squared in your original equation, well, then you want your x divided by 24 to all be squared in your new equation, right? You want to divide it by 24 first so that you have the value that you would have had originally, and then square it. What happens if you don't want to stretch, but instead you want to compress a graph? Well, I mean, just looking at these two equations, it's pretty obvious, right? Let's say this was your original equation, which is a 24 times stretch of this. And let's say you wanted to compress this by a factor of 24. Well, wouldn't that just go back to this? So when you want to compress any equation, well, then instead of dividing every x by 24, you just multiply every x by 24. It's just reversing the process. So a stretch and a compression are exactly the same thing. It's just if you want to compress it by a factor of 24, which means you want to shrink it so that 1 becomes 1/24, so that 24 comes in and becomes 1, and 72 becomes 3, 48 becomes 2. So as I said, instead of dividing by 24 for a stretch, you just multiply by 24 for a compression. Can you guess what you would do if I wanted to stretch this graph in the vertical direction? So these bottom points, instead of being at 2, would go up to 4. This top point at 4 would go up to 8. It would look sort of like, I'm just going to draw it by hand. So this point here would go to 4. This point right here would go up to 6, 8 would be up in here. All this garbage in here would be at the top here and down here, and this goes. So something like that. So everything's stretched by 2. Notice even the bottom part, since it's not at 0, it doesn't stay at 0. The bottom part is at 2, so it goes up to 4. So the whole thing will be higher than the original. If it were down at 0, well then that would be different, because stretching a spot at 0, it would keep it there. Stretching the part at 1/2 by 2 would go to 1, and so on and so forth. But the question is, what does the new equation look like? So now we have our original equation that we know already, which is y equals sine of log x over 24 squared base 2 plus 3. And we want to know how the heck are we going to make it so that for every x value I put in, the y value doubles. It gets twice as big. Pause the video, see if you can write down that equation, and come back when you're done and see if you got it right. Well, just like when we divided the x by 24 to stretch it in the horizontal direction by 24, well, we're going to do the exact same thing in the vertical direction. If we want to stretch by 2, we just have to divide the y value by 2. That way, the y value has to be twice as big in order to satisfy the equation, the original equation. For instance, if I originally put in x equals 1, well, I know that my answer is going to be 2.748 on this side. Okay? And that's going to equal whatever's on the right side. Well, if I don't want my y to equal 2.748, if I want it to be twice as much, well, then I need this left side to be y divided by 2. Because that way, y being twice as much divided by 2 will still satisfy the 2.748. So the fact that we're dividing y by 2 is allowing y to be twice as big and still satisfy that equation. So our new stretched out equation is simply y over 2 equals sine of log of x over 24 squared base 2 plus 3. There is, remember, that little issue of keeping the y isolated. So you are going to have to multiply both sides by 2 in order to get y by itself. Which means your final equation will be y equals 2 times the sine of log x over 24 squared base 2 plus 6. All right, the last skill to teach about for transformations is how to reflect it in, let's start with the x-axis. So how would I reflect this new equation, or this equation that I have here, which remember is this equation here. So how do I reflect y equals sine of log of x over 24 squared plus base 2 plus 3 vertically in the x-axis? Now, I did say vertically, and that's really important. We're doing a reflection up and down. So that should give you a huge hint of whether we're talking about the x value that we're modifying or the y value that we're modifying. Remember, every time we do things left and right in terms of translations or stretches, we're modifying the x. Anytime we do things up and down in terms of translations and stretches, we do things up. We do things in the y value. So if we're reflecting in the x-axis, if this is the mirror, that means this stuff is on its way down. It's going up and down. It is the y value that's going to change, right? And how's the y value going to change? Well, instead of 1 comma 2.748, that'll just end up being 1 comma negative 2.748. Every value on this thing will just become the negative of itself, right? If we had a negative number, well, that would reflect upward onto the positive. But it's the y value that changes from negative to positive or positive to negative. Pause the video if you think you know how you can modify this equation to make it the reflection in the x-axis, and come back to see if you got it right. Well, congratulations if you figured out. You just have to replace the y with negative y, right? Because each y value becomes the negative of itself. So if you want the y to be negative of itself, just multiply by -1 and it will be the negative of itself. So our new equation here is simply negative y equals sine of log of x over 24 squared base 2 plus 3. But of course, you guys know when we do things vertically, we want to isolate the y variable in the end. So now we need to multiply both sides by negative 1, and our equation ends up being y equals negative sine of the log of x over 24 squared base 2 minus 3. So now, even though this is the trivial case here, we're going to reflect it in the y-axis. Let's reflect our new equation in the y-axis. See what happens. That means that this dot here is going to come over to here, and this dot here is going to, they're going to switch each other. Now this is an even function anyway, if you notice. This is a perfectly even function. And so our final equation should actually be the same equation we started with. But why would that be? Well, let's look at the points that we have. Here we have a 1 comma negative 2.748. And when we reflect it, that's going to become negative 1 comma negative 2.748. What's happening is each x value is just going to become the negative of itself, but the y value is going to stay. So in our equation, we just have to replace the x with a negative x. Well, look here, we have x over 24 squared. Well, negative x over 24 squared is going to be the same answer as positive x over 24 squared, because anything squared becomes positive anyway. But the process is still the same, whether it's an even function or not. All you do is you replace the x with a negative x. So let's do that. Our reflected equation reflected in the y-axis will just be y equals negative sine of the log of negative x in brackets over 24 squared base 2 minus 3. Just make sure when you replace the x with a negative x, just put brackets around it. That way you won't run into any trouble, because whatever's happening to the x should be happening to the negative x. It's the same thing when we do translations and stretches. We always, the thing that we replace the x with, we want to put brackets around that. Let's summarize. For any equation with x and y variables, in order to translate to the left, we just take all the x values in the equation and we replace them with x plus however far you want to go to the left. Translating to the right, you go x minus how far you want to go to the right. If you ever want to stretch something horizontally, in other words, make every x value a times as large as what it was before without changing the y value, simply go to every x value in the equation and divide it by a, putting brackets around it, of course. If you want to compress, well, then you multiply it by a. And if you would like to reflect horizontally as well in the y-axis, well, then simply go to every x value in that equation and replace it with negative x. For vertical transformations, if you want to move things up, well, then you just go to every y value and you replace it with y minus the amount that you want it to go up. If you want it to go down, then you replace the y value with y plus the amount that you want it to go down. To stretch something vertically, in other words, to make all the y values twice as large as what they were before without changing the x value, simply go to every y value in your equation and replace it with y divided by the amount that you want it stretched. So if you want it tripled, replace all your y's with y divided by 3. If you want it 1/3 of the size, well, then just multiply by 3, so y times 3, which is really the same as dividing by 1/3, of course. And last but not least, if you want to reflect in the x-axis, so that's a vertical reflection, so all of your y values that were positive stay the same value but become negative, and all your y values that are negative stay the same value but become positive without changing the x values, then all you have to do is go to every y value in your equation and replace it with a negative y. One more thing to really keep in mind is that almost everyone loves for you to isolate y at the end. So you may have to do some extra work when you're doing things vertically. If you're replacing y with negative y, well, later on you're going to have to isolate y. So you might have to multiply both sides by a negative. If you're dividing y by a, well then at the end you might have to multiply both sides by a. If you're subtracting a from y, then at the end you may have to add a to both sides in order to isolate y. Now I'm going to finish off with another thing that becomes quite important if you're taking courses, and that's that when teachers, professors, textbooks ask you to list transformations, they always want you to list it with the kind of using the order of operations as well. So they don't want you to list the translations before you list the stretches, because if you list the translation, for instance, if you move something to the right 6 and then you stretch it by 3, well then really that's the same as stretching it by 3 and moving it to the right by 18. Because once you move it to the right by 6, if you stretch it by 3, well that's going to change how much you moved it to the right. So if we ever ask you to list the transformations, just make sure you list the reflections and the stretches and compressions, and then at the bottom list the translations. It's just doing multiplication before you do addition and subtraction.